Here's a video key for the first page of PSA 1. Very first question gave you perspective templates, and you were supposed to draw little structures with lone pairs on it and ask the question, is there a net dipole in the molecule? First molecule was, for an example, was ClF3. If you count up the number of electrons, if you do it right, there's two lone pairs and then these other fluorine atoms. Well, the lone pairs, if it's trigonal bipyramid, have to go in the equatorial plane. We talked about this many times. So here they are, and then all you have to then simply do is figure out where the geometric center of slight negative and slight positive is and draw the arrow. These F's certainly cancel each other out. Chlorine is in the middle, so that would be the slight positive. There's only one F in this direction, so we could draw an arrow from the geometric center of the slight positive on the chlorine to the geometric center of slight negative on the fluorine. These lone pairs would have an effect, but effectively this is the slight negative end. Likewise, if we did this with XCF4, again, xenon's in the middle, the fluorines are slightly negative. But many people just drew these arrows in. These are bond dipoles, the green arrows, going from the slight positive to the slight negative. And most people knew that the fluorine was slightly negative. But I asked for one molecular dipole arrow, not all the bond dipole arrows. You might include them in your mind's eye, but realize that given that these are square planar and for an equatorial system, for a octahedral system, the lone pairs are axial as opposed to the lone pairs being equatorial in the trigonal biplanar system. I think you can see that everything cancels out the bond dipoles. I left them in there. I didn't ask for them. Left them in there. And it's clear in this particular case that they cancel, and there is no net dipole, so there is no little red arrow here. Next question asks you to draw basically two water molecules, hydrogen bonding to this molecule. In this case, this is ethanol. So people did that reasonably well, but some not. So here's one water molecule here, and again, I could circle the slight negatives on each molecule. The O's are certainly slight negative. Put a little box around the slight positive ones. Only the H's that are directly connected to the O through a covalent bond are slightly positive. So here I can orient a lone pair on a water molecule. Could come up really close to a slightly positive H on another, and I drew these two dashed lines indicating that's a hydrogen bond. A lot of you just left off the lone pairs on the water molecules. Here's another water molecule. In this case, the lone pair on this O, that was on the ethanol, can get really close to the slight positive on water. So here's two different water molecules hydrogen bonding with this. Although we talked about it in class and everybody agreed they wouldn't do this, I had a lot of people doing this. Just because you see hydrogens, they don't necessarily participate as hydrogen bond donors. This hydrogen is not slightly positive. If you had circled all the slightly negative atoms, F, O, or N, this would not have been circled, hence this H is not slightly positive. Hence you would not make a hydrogen bond from water, from the oxygen and water to this H, because this is not slightly positive. Next example everybody did really badly on. I asked how you could show acetone, or this is not acetone but acetaldehyde, this molecule right here, interacting with water not through hydrogen bonds but through dipole-dipole interactions. That's what I specified. Almost everybody, put an H on water near this lone pair and put a dash line. Those are hydrogen bonds. That's not a dipole-dipole interaction. So the reason why we draw these dipole arrows on molecules, the net dipole arrows, is to help envision how molecules might interact with each other. So again, this is the only F, O, or N on this acid, on this molecule. That's slightly negative. That means that carbon is the only slight positive. So I could draw an arrow and it would look like this. I've overlaid it here in red. The dipole arrow, this is a permanent dipole, not a bond dipole. Permanent dipole, the slight positive center here and the slight negative center here. Now, if I were a water molecule, wouldn't it make sense interacting through a dipole interaction? That water would basically align its dipole in a direction that would allow for an attraction between these two dipoles. So here's the dipole on water, the slight positive end here, the slight negative end here, and this arrow part points directly to the slight positive on the original molecule that we had, which is the aldehyde. Likewise, another molecule could be up here, and you can get this alignment of dipoles, where the slight negative of this dipole is adjacent to the slight positive of this, and like the slight negative of this is adjacent to the slight positive of this. And in addition, we can see there's one probable other way we could align this. We could align this if I could take this molecule and flip it on top of this. The slight positive here, if it was overlaid on top of that, could interact with the slight negative here. So any of these I would give you credit for, but I did not give any credit for basically forming hydrogen bonds from water to the carbonyl O where the lone pairs are, because that's not dipole-dipole interaction. In the last example, I gave you two molecules. I actually gave you their lowest structures. This is CO2 and this is SO2, very similar molecules, and I asked which one is likely to have, the higher, let's say, melting point. Well, if you look at this molecule, how do they interact? That's one of the other questions I asked. Well, if there was another CO2 molecule interacting with this, notice that the geometric center of slight negative is right on top of the C. The bond dipoles cancel, so there is no net dipole here. So this molecule cannot interact with another molecule of CO2 through dipole-dipole interactions. The only thing that this could interact with to another CO2 molecule is LDFs. Whereas SO2, because it has a trig or planar geometry, I've got three clouds coming out here, and I gave you the lowest structure with the lone pair here. There is a molecular dipole in which I actually have the arrows printed wrong here. So I just corrected this. This is SO2. The center of slight negative. Positive is right there. The center of slight negative would be halfway between these two O's. Again, O is electronegative, FO or N, so there would be a slight negative here and a slight negative here. The geometric center would be right here. So now I can see I have two SO2s. They cannot hydrogen bond with each other because there's no hydrogen bond donor, but they have more going for them than simply London dispersion forces, because they have a permanent dipole. So this can interact, again, lining the dipoles, slight positive here, slight negative end of that molecule, aligning so that the slight negative of this molecule is near the slight positive of this one.